Welcome to Chapter 12 Wrap-Up. I have already posted two pictures of two different types of unit cells that these problems that we did not get to in class, the last part of problem number 30. So I'm going to make a little list of the ones we're going to do. So we're going to finish 30. I am going to do, finish 30. I am going to do problem number 31. I'm also going to do a couple of problems from the ACS that deal with these concepts. Numbers 7 and 8 on page 37. And then I believe there was one more I was going to do. That's 33C from your textbook. It deals with this same concept. So that should get us, oh, and there's another one. Practice exercise on page 485 in the book. So that'll give us enough examples to where we cement this idea about what we're actually trying to do here. What they want you to do in these problems is they want you to be able to relate the length of the unit cell, one edge, and these are cubes, so the length of a cube to the radius of the atom or atoms that make up the unit cell. Okay, so, and the derivation of from using Pythagorean theorem is different if you're doing a face-centered cubic, which is this one, versus a body-centered cubic, which is this one. So I'm going to do the derivation for both, and what we're going to end up with is a really simple equation that you're going to be able to just plug and chug into to answer these questions. So it's not going to be difficult, something you're just going to have to memorize. Probably going to be one question, if any, on the ACS using this concept, but I want you to be ready to answer any questions that are on that test. All right, so let's get started. The easiest one is the one at the top, face-centered. And this is what we're doing. We are saying, okay, I'm going to draw it up here on this figure. With the triangle that we are going to be using is this one right here. In fact, we're drawing a triangle on the face of the cube. When we do that, I know this length right here, that is the length of the unit cell. And in fact, the B part of the triangle, you know how it's A, B, and C, using Pythagorean's theorem. A and B in a face-centered in this triangle that we're drawing, because I can draw it on the face, A and B are the same. So if I come over here, and we're going to do it first for face-centered cubic, then C squared is equal to A squared plus B squared, Pythagorean's theorem. Well, A is equal to B, right? So C, and we have yet to describe what C is, and we're going to get rid of C in just a moment. C is equal to the square root of A squared plus A squared, which is equal to the square root of 2A squared, which is equal to the square root of 2A. Now, C. We are going to describe C in terms of the radii of the atoms. So if you look back up here at this triangle, these atoms are touching. We're talking about solids. And even though down here in the base body-centered cubic picture, they're still touching as well, but we have to draw a different triangle. In fact, we have to draw two triangles for the body-centered cubic. Your book really sucks at explaining this. Anyway, so back to the face-centered cubic up here. The length of C can be described as the radius of this corner atom plus twice the radius of the center atom. So that's 3R. 1, 2, 3, and then this last corner atom is 4. So in both the face-centered and the body-centered cubic, our C is always going to be 4 times the radius of the atoms that make up the unit cell, and that is equal to the square root of 2A. And so for any face-centered cubic structure, this is the little equation we're going to use. And you don't have to derive it, just plug into this. If you know the length of the unit cell, you can get R. If you know R, you can get the length of the unit cell. Okay, so that's our relationship between the two. Now, let me get a little more room here and try to derive for you the body-centered cubic. Okay, this is the deal in the body-centered cubic. I cannot draw a triangle on the face of this cube and catch all the atoms in the unit cell, or catch enough that it represents the atoms of the unit cell. So this is what you have to do for the body-centered cubic. You start off by talking about the base down here at the bottom. So you're talking about essentially the floor of the cube, if you will. And on the floor of the cube, or the base of the cube, we're going to have a triangle that's where you have A, and then along a flat, this is on the bottom, then you have C, essentially, okay? Well, this is an equilateral triangle, so A is equal to A, because it's both the cell length. So C is equal to, just like we did up here, is equal to the square root of 2A, okay? So that is no different from the face-centered cubic, but we haven't drawn the triangle we really need, but we're going to be using part of that triangle. So this is what we're going to do. We are going to now take the triangle that goes up, and in order to catch that atom in the middle, our new hypotenuse goes through that center atom like this. So it's what they call that the body diagonal. So you have A, C, and the B, it becomes, and I just have to draw a line to it, becomes the hypotenuse from that bottom triangle. So in this triangle, C is equal to square root 2A, but in our new triangle, that's actually B, and it is equal to the square root of 2A. Now your book makes that substitution, but does not explain the fact that you're actually doing two triangles in order to do this. So very confusing, and I had to ask a couple of people myself until I finally got it and was able to explain it to you. So, new triangle. The up side is A, that's the length of the unit cell, and B is the square root of 2A, and C is again going to be, so if I look at this body diagonal up here in this picture, it's 4R again. Radius of this, twice the radius of the one in the middle, radius of the corner atom. So C is still equal to 4R, which is equal to the square root of A squared plus B squared, but I'm going to substitute this for B. So it's going to be square root of 2A squared, okay, which is equal to the square root of A squared plus 2A squared, which is equal to the square root of 3A squared, and so therefore 4R is equal to the square root of 3A. So we're going to use this one for face-centered cubic, and we're going to use this one for body-centered cubic. And that's the take-home. That's what we're going to plug into each of those questions that we're going to do. But that's how you come up with the equation. And from there, it's easy. It's just understanding how that works. All right, so let's go ahead. We're just scrolling up here to see which ones I said I would do. 30, 31, 33C, and then those the practice question. Okay. All right, so let's finish. First, let's finish number 30 that we did not finish in class. So 30 from the back of chapter 12. What we did when we did 30 in class was we found the volume. And it was equal to 78.7 or 79 angstroms. And they want to know what is the radius of the atom, okay? And it is a body-centered cubic structure. And let's see, number 30. Let's make sure. It is sodium metal. Okay, so we used that in getting our volume. We used the fact that it was sodium. So what I need is if I'm trying to find R, then I need the length of the unit cell, which I can get by taking the cube root of the volume. Okay, is equal to A, right? And when I do that, when I take the cube root of 78.7, I get, I've written down here, 4.3 angstroms. Now I'm rounding a little bit, but that's what I've got written down, and I don't want to go through it again. So 4.3 angstroms is the length of the unit cell by taking the cube of the volume. If I take 4.3 and cube it, or if I carry this out a few more decimal places, I would get my 78.70. It's a little bit different than 78.7 if I cube 4.3 because I'm rounding a bit here. Anyway, cube root of the volume gives you the length of the side. So now we just plug it in for body-centered cubic. So 4r is equal to the square root of 3 times 4.3. R is equal to the square root of 3 times 4.3 divided by 4. And when you do the math, you end up with 1.86 angstroms as being the radius of the atom. 1.86 angstroms. And that's the answer for the rest of 30 that we did not do. Okay, let's go on to 31, which is the one that Kristen wanted me to do at the beginning of class, and she said her tutor couldn't figure it out, and I understand why. After I finally got it figured out myself, they just don't do a very good job. This is a face-centered cubic, okay, system. It is iridium. And they give you they give you the length of the unit cell, so it's 3.833 angstroms. Okay. And they want you to calculate the atomic radius in A. So they want R. And it's face-centered cubic, so we're going to use the relationship between R and A, which is 4R is equal to the square root of 2A. So R is equal to square root of 2 times 3.833 divided by 4. And so R is equal to 1.36 angstroms. Okay, so far in both of these problems we've dealt with an element where every atom is the same. We're going to do an example where we have two different elements, an ionic solid. Nothing's going to be different. It'll be essentially the same. We just have to take into account that you'll see. All right, and then 31b asks to calculate the density of iridium. So let's go ahead and work that one together because I know you've had some difficulty with, you weren't quite getting that when we did it in class. So density of iridium. So what do we want? So on B, what do we want our units to come out in? I'll extend the page again. Grams per centimeter cubed. So I'm actually going to move down a little bit. So I want, in the end, I want grams per centimeter cubed. So what do we have so far? We have the length of the unit cell. Okay. I can get the volume of the unit cell from that. I am going to use the fact that this is iridium to get grams per mole. It's face-centered cubic, so I have 4 atoms per unit cell. Remember, 6 faces times a half an atom each equals 3 atoms on the faces, and then the corners, 8 of them times an eighth give you that 1 atom. So there are 4 atoms in the face-centered cubic. All right, so we want let's get the grams in there first. Always focus on the question, focus on the units that you need. So I need some grams, and they need to be on top. All right, so I'm going to look up iridium on my periodic table, which keeps moving on me. Here it is. All right, iridium is 192.22 grams per mole from the periodic table. Molar mass. Okay, can get rid of moles using Avogadro's number. All right, and then I can atoms. Definitely going to have to erase this. Okay. Moles are gone. Now get rid of atoms using this right here. 4 atoms per unit cell. All right, so now we've got our grams where we want them. I need to get volume in there. So I'm going to take my length of the side from up here. So the volume is going to be 3.833 cubed. And that's going to be in angstroms. So 1 unit cell has this volume, 3.833 angstroms, and then I'm going to cube that. All right, so unit cell goes away. And all I have to do now is switch from angstroms to centimeters cubed. So let me do a little more erasing. Okay, you don't need this anymore. So I can string it all together. So we've done the conversion between angstroms and centimeters cubed. All right. So for those of you who are still a little weak on this, when you're doing cubic, try not to think about the cubic part. Just do the relationship between angstroms. 1 angstrom is 1 times 10 to the minus 8 centimeters. And then cube the conversion factor. And now angstroms are gone, and I've got grams over centimeters cubed. So I have got the correct units, and now I just plug it in on my calculator to get the correct answer. All right, so let's do that. Do it along with me. Make sure you can get it. Now I get 22.7 grams per centimeter cubed, and that is the correct answer. 22.7 grams per centimeter cubed. And that's the density for 31B. Okay, I'm going to go back up. We're going to do 33. We're going to do part of 33. Let's see what 33 says, because you've got the answers in the back of your book. It asks you to, it's aluminum metal. Now it says cubic close packed structure, but in parentheses it says that that is in fact a face center cubic. So you've got a face center cubic in 33. How many aluminum atoms are in the unit cell? So we've already just answered that in the previous question. We've done it a couple of times, so you can do that. What is the coordination number of each aluminum atom? We'll do that. And then C, estimate the length of the unit cell edge from the atomic radius of aluminum. So they're giving you the R, and it is equal to 1.43 angstroms. I'm going to do C first, and then we'll come back to B. And then it asks you to calculate the density in D, and I just did it up here. You have the answer, so I'm going to let you try that on your own. So we're going to do B and C of this problem. Let's do C first, because it's the same thing we just have been working on. Face center cubic, so 4R is equal to square root of 2A. Plugging in 4 times 1.43 divided by square root of 2 is going to give you the length of the unit cell edge, A. Okay, so 4 times divided by syntax error. And I get 4.04 angstroms as the length of the unit cell, which is the correct answer for B. C, rather, sorry. For B, it's asking you to, what is the coordination number of each aluminum atom? Okay, now you can't use that little equation that we had, which was the ratio of the cations to the anions is equal to the coordination of the cation to the coordination of the anion. You cannot use that equation because we don't have a formula. So what we really need is a picture that will help us see this, all right? Well, so it's asking you to look at the picture and figure out how many closest neighbors there are. So I'm pulling a picture in from the notes to help us with this. Let me bring this down right here. All right, so we have a face center cubic structure, which is this structure here on the right. So if we talk about, it's always easiest to look at a center atom. So if you look at this atom right here, okay, in the middle, right there, you can see that it has 6 closest neighbors in the same plane with it, okay? But then above there, then there's going to be a layer above and below it, okay? So then maybe it's easier if we start with this center atom, and it has its 6 closest neighbors, okay? and then underneath it, this center atom is in contact with 3 atoms below and 3 atoms above. So 6 in the plane plus 3 below, 3 above, and 3 below. Okay, and that gives a coordination number of 12, which is very large. This is a very dense packing, cubic close, the cubic close packed. Okay, so that's B on 33. All right, the next one I want to do is one where all the atoms aren't the same, and that is the practice on page 485. Okay, so we're going to go to practice problem. So it's one of those in the box, but it's not the one they go through in the box. Page 485. It's one where they give you a similar question and then you have the answer there. All right, so let's go to that. Okay, this one is cesium chloride is the substance. So we no longer have an element, so we're going to have to deal with 2 different radii. Look on page 482 where they show you the picture of this unit cell. If you look at page 482, you see a picture of the unit cell. And in that picture on page 482, it shows a primitive unit cell, a primitive cubic unit cell. But because the motif, remember each lattice point in the unit cell is where the motif goes, and the motif of what we've done so far has been 1 atom for each lattice point. Now we have 2 atoms. Oops. Okay, so if you look at the picture, it looks like a body-centered cubic, okay, because the motif is 2 atoms instead of 1. If it was 1 atom, then we just have an atom at each corner. All right, so anyway, it's body-centered cubic. So we're going to be using our equation for body-centered cubic, which is 4r is equal to square root of 3a. Now, let's read what they're asking you to do in that. I know it's cesium chloride, but let me go back. They want you to get the length of the unit cell. And they give you the length, the radii of both the cesium ion, cation, and I'm going to show you how this works with 2 different ions, and chlorine is 1.67. All right. So instead of doing 4 times 1 number, we are going to do 2 times the cesium plus 2 times the chlorine. So you're still going to do 4 times the radius. It's just different. But let me draw you a picture and show you why it's that way. So when I do my body diagonal triangle, okay, that we talked about, then in the middle I have the cation, I believe it is. Let me look and see just real quick. The anions, the negative ions are always going to be bigger. That's how you can distinguish, okay. It's not page 480. Yeah, it is. Sorry. Okay. In the middle is cesium. And on the corners is chlorine. Okay. So chlorine's on the corners. So this is cesium, and these are chlorines. So we're still going to use 4 times the radius, but it's going to be 2 chlorine radii. So it's going to be 2 times Cl minus R. Or another way to write that would be 2R for Cl minus. Okay. Plus, in the middle, twice the radius of the cesium atom. So twice the radius of the cesium atom. And that is going to be equal to the square root of 3a. So pretty easy. 2 times chlorine, 1.67, plus 2 times 1.81, divided by the square root of 3, and that is going to be our length of our cell edge, and that comes out to 4.02 angstroms. All right, so even when you have 2 atoms, pretty easy to do. All right, okay, the last thing I think I said I would do is a couple from the ACS book. which will get you ready for these questions should you encounter it. So numbers 7 and 8 on page 37 in the ACS book. And that'll finish us off. So go ahead and find those. Number 7 is just going to be another dimensional analysis where we're going to go through that one together. And then number 8 is one of these types of problems. All right, so number 7, page 37 from the ACS. Okay, it's asking you to get the mass of the unit cell. And it gives you the fact that it's lithium and that it is, hold on, so we're dealing with lithium. They want the mass of the unit cell, and they tell you that it is body-centered cubic. I'm just going to double check the wording on that, because I did this problem on paper yesterday. Okay. Lithium crystallizes body-centered cubic. What is the mass of 1 unit cell? Okay. So, we don't need this equation up here. We're not relating edge and radius of atoms. We're just doing some dimensional analysis. So what, if they want mass of the unit cell, our units that we want to end up in, mass, grams per unit cell. Okay, well, it's lithium, so let's start with the grams of lithium off the periodic table. Grams of lithium is 6.941. 6.9, let's start it down here, so I'll make sure, but this is the units I'm trying to get to, okay? So 6.941 grams per mole times Avogadro's number, well, divided by Avogadro's number. Okay, it's body-centered cubic, so I have 2 atoms per unit cell. And I think I'm done because I've got grams per unit cell. So when I do the math, I end up with 2.3 times 10 to the minus 23 grams is how much 1 unit cell weighs, and that is the correct answer, no, part B. All right, for number 7. All right, number 8 is one like the geometry one. Copper crystallizes in a face-centered cubic if the edge is 351 picometers. What is the radius? Now, the nice thing is that you can stay in picometers because the answers are in picometers or picometers, whatever. For a face-centered cubic, 4r is equal to the square root of 2a. So r is equal to the square root of 2 times 351 divided by 4, and I get close to the right answer. When I plug those numbers in, I get 124 picometers, and the correct answer is A, which is 128. I don't know how they get 128. It must be a typo. But easy peasy once you know these quick little formulas, but it is not straightforward as to how they are derived. All right, so I think that does us. We did 30, 31, 33, we did the practice problem, and we did the 2 from the ACS. This concludes our wrap up of chapter 12.